Good morning, friends. So, welcome back to a new topic, nuclear fission. So, today we will discuss the energetics of nuclear fission. That is, why nuclear fission and what is the condition for spontaneous fission in a nuclei. As you know, in 1932, James Chadwick discovered neutron. This discovery of neutron induced the research in nuclear physics. So scientists tried to bombard this neutron with various nuclei, and they studied the reactants, they studied the products, and they studied different types of reactions. So one of the noticeable observation was this irradiation of neutron produced the beta minus reaction in various nuclei, in different nuclei. So they tried what is the importance of this beta minus process is that one of the neutron is transformed into a proton by producing an electron, a negative charged electron. That means the nucleus itself is transforming into another nucleus, or the atom is transformed into another atom, the next higher atom with the next higher atomic number. Okay, so in this way, the scientists found that it can produce the novel atoms, the newer nuclei. So the attempts to produce transuranic elements means the elements beyond the uranium, which was the naturally available, the stable elements at that time. So they tried to produce the transuranic elements by irradiating this neutron with uranium with atomic number 92 to produce this beta by the way of this beta minus process. So the result was a little bit confusing. They could observe the transuranic elements, the property of a greater nuclei, but closely studying the results, the products, the resultant products, they found that the property of the newly formed products are very similar to that of the barium. So they assumed that this should be a element inside the group of elements of the same as that of the barium, but more depth studies showed that it was nothing but the barium itself. So it was a little bit confusing and amazing results, since they tried to produce a larger nuclei or larger atom, but the result was an atom with a lesser atomic number, almost with half a mass. So scientists studied in depth with the different other nuclei also. And finally, they concluded that it was nothing but the fission of atoms into the fragments, and the nuclei with lesser weights are formed. Okay, so you can see one example. The neutron is bombarded with the uranium nucleus, and they are fragmented into two, and new neutrinos are produced, and with some extent of extra energy is also produced. So this is the fission. So this kind of fission is occurring in this kind of large nuclei when it is bombarded with this neutron. So why the nuclear fission, or what is the advantage of fission? So you can see that this binding energy curve, we found that this binding energy curve, the peculiarity of this binding energy curve, initially it is increasing and it is maximum for the iron 56, and after that it is gradually decreasing. It is nearly constant, but it is gradually decreasing. So this is the binding energy per nucleon. So when we go to the left side, what is happening? The binding energy per nucleon is increasing. Similarly, when we goes to the right side up to this position, up to this iron 56, again this binding energy per nucleon gets increased. So what is the meaning of the binding energy increasing? The binding energy increasing means that much energy is released and a more stable nuclei is formed. So there are two ways to form the stablest nuclei. For smaller nuclei, we can combine the nuclei up to iron 56 and the energy is released and a more stable nuclei is formed. So this combination of nuclei is known as the nuclear fusion. And on the right side of this point, this iron 56, we can fragmentize, or we can fracture the larger nuclei or fission the larger nuclei and produce the smaller nuclei, the resultant nuclei, and this binding energy per nucleon gets increased and that much energy is released, and they form more stable nuclei. So these are the two ways. In both cases, the energy is released. So what is the importance of this energy? This is a great extent of energy compared to other modes of energy harvesting, and we can utilize this energy in our own convenience ways for producing the electricity, for producing the atomic bomb, and like that. Okay, so we'll see the energetics of fission with taking the uranium-238 example. Okay, so when we divide this uranium-238 into almost two equal fragments of atomic mass 119, we will see the uranium region. This uranium region has the binding energy per nucleon of 7.6 MeV per nucleon. Here at this point, this is approximately 7.6 MeV per nucleon. And the resultant nuclei with nearly the atomic weights 119, and they have the binding energy per nucleon of the order of nearly 8.5 MeV, nearly 8.5 MeV per nucleon. That means by forming this nuclei from single nucleons, here this minus 7.86 MeV into 238 MeV. For the case of uranium-238, this is equal to minus 1,809 MeV energy is released. But at the same time, when these resultant nuclei are formed, this minus 2033 MeV energy is released. Means when the resultant nuclei is more stable by nearly 214 MeV energy. In other words, when the uranium is split into these two nuclei with 119 mass, 119 atomic unit mass, this 214 MeV, nearly 214 MeV is released. And they are that much stable than this uranium-238. So where goes to this released energy? This released energy appears in various forms, like the kinetic energy of fragments and the energy of neutrons, beta particles, gamma emission from the fragments, etc. But the 80%, the most part of the energy is with the kinetic energy of the fragments, and that we are harvesting and that we are utilizing. Okay. So this is the energy advantage behind the nuclear fission. But we know that Other than the nuclear fission, there are different kinds of reactions which may occur in this kind of nuclei. For example, in uranium-238, the more prominent reaction is the alpha decay, which also produce the stable nuclei by reducing the number of neutrons and protons, and it comes to the stability belt. So the half-life of this alpha decay is T halves equal to 4.5 into 10⁹ years, but the half-life for the uranium-238 is 10⁻16 years, means much larger than this alpha decay. That means this stability of the nucleus, this nucleus, uranium-238 nucleus, against the spontaneous fission is much larger than this alpha decay. In other words, this alpha decay process is more prominent in uranium-238 than this uranium fission of uranium-238. So what is the reason behind it? Here, the reason is, you can see, so this is the potential well, the nuclear potential well, where this is representing the nuclear energy. We know that this nuclear energy is always attractive one, the nuclear force is always attractive one, and this is the negative energy. And here, so here we going from right side to the left side on the binding energy curve, or climbing the binding energy curve. 214 MeV is released. So we can assume that this nuclei is going to just splitting, and at this moment, just before the splitting, there is 214 MeV is released, and this nuclei is just here. The nuclei have to attain at least some nearly this much energy, this difference in energy, to overcome this barrier. Means this barrier, this is the Coulomb barrier, and to reach here. Just overcoming, just after this barrier, this Coulombic repulsion between these two nuclei will drive this nuclei far apart with much energy. Okay, so what is this Coulomb barrier? So this is the Coulomb barrier, means when they are just going to splitting, they are actually, we can assume that it is just like two nuclei are inside a barrier or inside a boundary. So each nuclei with half mass, that means the radius of each nuclei inside this large nuclei is 1.25 into 119 into 1 to the power 1/3. That is 6.1 Fermi is the radius. So we can calculate the potential energy, the Coulomb potential energy, that is 1/4πε0 Z1 Z2 E squared by R. So substituting these values, we get this is 250 MeV. So this 250 MeV is the Coulomb barrier for with two nuclei with atomic mass 119. Okay, S equal to 190. So this is the Coulomb barrier, but the nucleus is just at this position, and there is approximately there 36 MeV energy is needed to overcome this barrier. Okay, so this is the reason, because this half-life for the uranium-238 is this much, and this much larger than this one, and this alpha decay is more prominent in uranium-238. So this is the potential barrier curve representing the spontaneous fission of uranium-238. You can see now our uranium-238 nucleus is at this position with 214 MeV. this has to attain this much energy, that is nearly 36 MeV, to overcome this barrier and to reach at these positions. These positions means they are get separated and now they can move far apart. Okay, so this activation energy is for different nuclei is represented in this graph. Here you can see this bold curve is the activation energy curve using the liquid rope model, and this light curve with this light colored curve is the activation energy curve including the shell effect, the shell model effect. That is the corresponding to the magic numbers, they are more stable. That is why at those positions the nucleus are having with maximum activation energy. Okay, and you can see at this position, nearly this 290, 300 position, there is zero activation energy. Means the spontaneous fission can occur without any energy or instantaneously happen this spontaneous fission. Okay, so now assuming by stretching the nucleus, we assume that the spherical nucleus is going to the ellipsoid one, and what happens to the binding energy terms? We can see the volume terms, the volume remains constant and there is no change in volume terms, and the surface terms is modified. We know that as the sphere is going to the this ellipsoid one, the surface area gets increased and the Coulomb repulsion between these nuclei, these two segments, two fragments, gets decreased as they are going apart. So this is the change in these first three terms. This is the terms from these are the terms from the liquid rope model. So what is the result in this delta I, the change in binding energy, net change in binding energy? So the surface term, we already mentioned that this volume term does not change, but the surface term is increased by this much, 1 plus 2 by 5 epsilon square plus, like that, since surface area gets increased, and this Coulomb term is decreased by this much into 1 minus 1 by 5 epsilon square plus this much, since they are more at far distant, they are more far away. The two fragments are more far away compared to this spherical single nuclei. Okay, so taking the difference between this spherical one and this ellipsoid one, this will be like this one, minus 2 by 5 as a to the power 2 by 3 plus 1 by 5 a z square a to the power minus 1 by 3 into epsilon square, where this epsilon is the eccentricity. Okay, we know that this eccentricity is 0 for the sphere and it is larger than 0 for this ellipse. Okay, so from these two terms we can find what happens to the binding energy by the stretching or by the stretching of the nuclei into two fragments. So from these two terms we can see that this term or this binding energy gets increased when this Coulomb term or this second term is larger one. Okay, so binding energy increasing is the our favorite condition. So the condition for the spontaneous fission or condition for the favorite condition, our favorite condition is this term is larger than this one. That means 1 by 5 AC into z square a to the power minus 1 by 3 is larger than this one. So substituting these values of this AC and AS here, we will get it as the z square by a greater than 47. So this is the condition for the spontaneous fission. Spontaneous fission means fission, the nuclear fission without supplementing more energy or without supplementing more activation energy. So if the nuclei satisfy this condition, then the fission will occur readily, instantaneously, without any much more energy. So this is the experimental curve for the z square by a versus the half-life. So we can see that this z square by a condition or z square by a case is not obtained experimentally, but we can extrapolate this graph to the z square by a is equal to 47 condition. Okay, so it will be much this rightmost position, and extrapolating this curve to the y-axis, the half-life will be obtained as 10 raised to minus 20 years. 10 raised to minus 20 year half-life means the fission occur readily or within a few microseconds the fission occur. Okay, but we don't know such nuclei. We don't know such existing nuclei. A nucleus with A is equal to the atomic mass A is equal to 300 and Z by A is equal to 0.4. We will obtain this Z square by A is equal to 48. So we already had mentioned that this A is equal to 300, the 300. In the previous curve also, the activation energy curve also, S equal to 300 was the activation, the zero activation energy position. So this is this calculation also satisfy, or this calculation also match with those activation energy curve. Okay, thank you.